Oh,
I'm doing well. I'm doing well.
great.
Yeah, I just got back from a week in Puerto Vallarta. So
Oh, that
having
sounds
having nice
nice.
young people bring me drinks on the beach.
Yeah, I'll sign up for that.
Okay. All right. And looks like we've got the recording going. So I'm ready to start whenever you are, team.
Yeah, we'll start right now, sir.
Okay, let's do it.
All right, we have a presentation, so we'll present that. And along
Okay.
with that, after the presentation, we can have any feedback or any concerns. We can address the concerns if you have any.
Okay. Yeah. And then we'll just take a quick look at your rocket
Yes.
and kind of just go nose to tail with it. But yep, over to you.
All right. So we are team number 56, Trust MIT from Manipal Institute of Technology, India. And we have our rocket named Agni Astra. This year, we are participating in the 30K COTS category. This is our first time in the category, and we have transitioned from the 10K COTS category to the 30K COTS category. Our rocket has a diameter of 12.4 centimeters. Are you able to see the screen, right?
Yeah, I hear you
Yes.
fine. See everything. Yeah.
All right. So our rocket diameter is 12.4 centimeters. Its weight mass is around 32.21 kgs. It reaches the maximum velocity of 1.83 Mach, and which is around 2055 feet per second. Our rocket's predicted apogee is 30,085 feet. And we have two parachutes. We'll come to the recovery part later, with which the ground velocity will come out to be 7.5 meter per second. Moving on, this is our rocket. It stands 319 centimeters tall. So next we have aerostructures, and Dhruv will be able to explain it.
Hello, sir. I'm Dhruva, and I'll be explaining about the structures, aerostructures part of our rocket. So our rocket consists of three bays. That is our motor bay made of carbon fiber. All the bays are 2 mm thick, and the motor bay is made of carbon fiber. The drogue bay is made of glass fiber, and the main bay or the recovery bay is made of glass fiber as well. Uh, the motor bay and the drogue bay are coupled using a carbon fiber coupler, and the drogue bay and the main bay are coupled using the avionics coupler. The avionics coupler houses all the avionics and the electronics components of the rocket. Finally, coming to the nose cone is made of carbon fiber as well, and the nose cone houses the payload of the rocket.
So next we have fins, and yeah, yeah. So this year we have gone with a hexagonal cross section. Our fins are 8.5 centimeters tall, so the height is 8.5 centimeters, and the root chord is 220 mm. And there is a 0.5 mm fillet on it. And we have also done flutter analysis on it. We have done FSI. We have done transient thermal. We have also used FinSim and the Apogee rocket calculations for the flutter, and the flutter velocity comes out to be around 1560 meters per second, which is around 5,118 feet per second. We have a factor of safety of around 2.49. And our velocity off rail is around 148 feet per second. Coming to the recovery, we have uh, dual. We are going to use a drogue parachute and a main parachute to recover our rocket. The drogue is going to deploy at apogee, and the main will deploy at around 1,500 feet above the ground level. So we have realized that at 30,000 feet, the recovery using black powder is quite challenging.
Yes.
So what we had done was that we had figured out the setup where we had referred to the test done by Jim Jarvis in his article, and from that we had found out that this setup works quite well. So we have our charge well. On it we put a black powder. then we put some recovery boarding, and then we seal it with an epoxy plug. And to prove it's working, we have also done vacuum test on it with it. So we are
Good.
quite confident on that. We had also shared the video with you regarding the vacuum tests for the high altitude ejection.
Okay. Right.
Yeah, we can also show you the setup later. We'll carry on now. So as you can see, this is the shock cord arrangement. For the drogue, we have a total of around 13 to 14 meter of shock cord. And for the main, we have around same 12 to 13 meters of shock cord. And the drogue bay charges are going to be 5 grams and 6 grams. And similarly for the main bay, charges are going to be 5 and 6.
Okay.
Yeah, coming to the nose cone, it's our tangent ogive nose cone with the fineness ratio of 5:1, and the nose tip has a fillet of 1 mm, and which also houses our payload, which is a CAMSAT of 10 centimeters diameter and 30 centimeters tall. And the tangent of the shape was chosen after several iterations and then CFD simulations of 6 different shapes, and then we narrowed down the nose cone shape to be tangent ogive. Our rocket spends nearly 9.4 seconds in the supersonic regime. So we found out that the tangent ogive gives the least drag in the supersonic regime, and that is why we have chosen this design. So these are the drag plots for different nose cone shapes. And we found out that in the supersonic regime, which we are really concerned about, that is tangent ogive gives the least drag. So that is why we went ahead with that. Moving on to propulsions, Virnach.
Yeah, hi. So the motor we are going with for this year is Sesroni's N5800. So this motor has a total impulse of 20,146 Newton seconds, and its burn time is 3.5 seconds. Earlier we had in the initial design we had chosen O3400 by Sesroni again, but due to problems with the availability of that motor, we switched to this. The motor bay, along with the motor, it houses several other components. Firstly, starting from top, we have the thrust plate, which connects to the motor head using an eye bolt, and it's the component that distributes thrust throughout the rocket fuselage. We have damper, which sits around the forward closure of the motor, and its basic job is to dampen out lateral vibrations of the motor. The motor is centered using 2 centering rings, and they are strategically placed so that we can mount rail buttons on them. So the distance between the centering rings is the same distance that the rail buttons have. And we have stringers running longitudinally. So there are 4 stringers. The stringers, they are used for fin attachment as well. We have fins welded to the stringers. And in the end, we have a retainer that supports the motor from the aft end.
Okay. So yeah, good. That answers a question for me. So you're tying, your fins are actually going through the wall, tying into your stringers. Am I understanding that correctly?
Yeah.
Okay.
I can show you the assembly right now. So you can see the assembly here.
Oh.
This is the slide assembly. We have the motor inside this. So we have aluminum 6061 fins. We can use an aluminum. This is basically TIG welded to the stringers using an ER4043 filler. So this is seam welded, so it ensures proper structural integrity. And these are the 2 centering rings. One is the lower centering ring, and this is the top one. These are 84 centimeters apart, and then we also have the rail buttons on this, which are mounted using an M6 bolt.
Once we slide in the assembly, we'll be filleting it as well on the body tube, the fins.
Okay, very good.
Continuing. Next, we have avionics.
So moving on to the avionics part of it, the avionics bay is sitting in a coupler between the 2 recovery bays, so between the main and the drogue bay. So right now we have a stack bay system which has 6 boards stacked on top of each other doing different functions. So we have our PDB and then our microcontroller and our sensors. and GPS telemetry, and and also our MOSFETs for firing the recovery events. Other than that, we also, for redundancy, we also have our COT systems, which are the featherweight and RRC3, which is our altimeter. Okay, so this is the bay for this year. So we have our 6 boards. That's our stack, and so we'll be sending. We have a MOSFET board right here to send pyro charges to the upper bay and the lower bay. We can see the wiring for the E-match. We just placed one just to show you for now. I don't know if it's picking it up, but so we'll route it through. We will properly secure the wires in place. All the loose wires right now, we will zip tie them so that there's no loose wires. Apart from that, we also have a camera which is facing towards the horizon. It has an FOV of 150 degrees, and the cutout for the camera will be placed at the static band of our bay, and the static band will also house the holes for our pull pin switches.
Okay.
So that's our setup right now, and yeah.
These are the wiring diagrams for the COTS RC3 and the flight camera. And we also have the SRAT flight computer wiring diagram. This is the payload for this year.
Okay, just real quick, tell me about your batteries for your avionics. If you're going to get to that later on, then I'll just wait till you get there. But
should we get to that later?
Yeah, we can do that later on.
Yeah,
Okay.
let's just go to the whole PPT and
okay,
then
we keep going then. Yep.
Okay, so the dimensions of the payload is 10 centimeters diameter and a 30 centimeter long, and it's nested in the nose cone. The payload of this year is a intelligent 3D vision system, which actually do 3D tracking and pose estimation, and also the angle calculations from the object. We are basically using a high computer graphic processor, Jetson Nano board, for all the processing on board, and we are using a 6000 mAh lithium ion battery to power our whole system. So the idea is to simulate the algorithms in a aerial intelligent systems where we regularly face high vibrations and high Gs.
Okay.
And next we have the CONOPS for this year's rocket. This is the slide. This is the flight profile graph. So that is about it for the PPT. We can move on
Okay.
towards
Okay. Yeah. So let's talk about your batteries here. What kind of batteries do you got in for all your equipment there?
So we have 2 lithium ions powering the lithium ion batteries powering the SRAT flight computer.
Okay.
And then apart from that, we have a 9-volt battery for the RRC3, an
Yeah,
alkaline battery.
Yeah. So
what
that
it-
connector. Yeah.
Yeah. And as for the featherweight, we have gone with what is prescribed by the manufacturer. It's a LiPo battery. However, it's 370 mAh 1C. So it's standard, whatever has been prescribed. So we don't want to change that for our COT systems.
Okay. That's good.
Is there anything else, sir?
How about your experiment? What are you using to power that with?
Yeah.
Enough. So
Not enough.
yeah, sorry. So we are also using a 6000 mAh lithium ion battery. That's 7.4 volts, like 2S battery, and that's going to a PTB for like power distributions processing. Only one battery we are using, single.
Okay. All right. That's good. So what are you using for your shock cords? What
We have
material?
these. Yeah, I can show you the chocolates here. Is it maybe no?
Parth, you are muted.
Okay.
Yeah, so we have these.
You're on mute again. I can't hear you.
Yeah, so we have these half-inch Kevlar shock cords. They are
Okay.
rated for around 6,000 pounds, and this is going to be our main parachute, which is protected using Kevlar. And
Okay.
we
And how? Yeah. What's your chute diameter for your main?
chute diameter for the main is 84 inches. That
Okay.
is going to
Makes
bring down
sense.
the rocket to 7.5 meters per second on ground. And we also have swivel links attached to both the main and the drogue parachutes. The drogue is a 24-inch parachute, which is going to bring the rocket down to 107 feet per second, which is also protected using a Nomex blanket.
All right.
Yeah.
Okay. Very good. And show me your coupler where you have the attachment points for the for your recovery harness.
So on the coupler, we have these eye bolts
Okay.
over here, this one and the other one.
Okay.
The
Yeah.
eye bolts are nutted and they will attach to the shock cords.
Okay.
And here are the charge belts as well.
Yes. Saw that.
That looks solid.
Yeah. Very,
This is
very
our
solid.
movement for
Yeah.
the fuel.
Okay.
And here we also have our CANSAT, on which we have the threaded rod, which extends to the top. So
Right.
this goes inside the nose cone. And from the top, we can attach our nose tip. The nose tip also has a 1 mm fillet at the top to for manufacturability and also to prevent any mishaps, because that can be real sharp. Even for the fins, we have a 0.mm fillet because they follow a hexagonal cross section. We didn't want them to become very sharp, so we also, for manufacturability as well as safety, we have that.
And your CANSAT stays attached, it's not deployed?
No, it's a non-deployable payload this year.
Okay.
And the on the nose cone bulkhead, we also have this attachment attaching to the shock part.
Okay. Okay. And are you? Looks like are you using shear pins there?
Yeah.
Where you're?
Just a second, we're getting the couplets.
Okay.
Yeah. So these are the body tubes for this year. These are all of the body tubes have been manufactured in-house. Basically, all components have been manufactured in-house. We actually started with wooden mandrels at first, but then we moved to 3D printed mandrels because we were running into issues with moisture into the wooden mandrels, so they were changing lengths and diameters. So these were our 3D printed mandrels, which gave us a pretty good finish in the end.
Yeah. No, it looks
This is
good.
the nose cone shoulder. Yeah, so we have this is our avionics coupler. It's a glass fiber coupler. We have
Okay.
our switch band in between, and this is our main bay, which attaches in from here, and then yeah, and then we have our rope bay attaching from the other side, and we are going to have shear pins over here. This is the opposite side actually, but we are going to have shear pins over here and over here, which are going to separate.
Okay. Using 4 shear pins on each side then?
Yeah, 4 shear pins on each side.
Okay. And what kind of switches are you using?
Which is
So we're going with full pin switches from Lab
Oh,
Rat
full pin?
Rocketry.
Yep.
Yep.
Okay, good. Those, no complaints there. That's what I use personally, so myself. So
Yes, sir. We've been
not that that's definitive, okay, but yeah, those are good stuff.
sit down.
Yep.
all right. This is the motor bay. So this is again a carbon fiber body that has been laid up using the same thing. This is the drogue bay coupler, which attaches to the motor bay. So we'll be having thrust plate holes here, and we have fin slots at the bottom. So the entire motor bay assembly we have sliding assembly sliding from the bottom, and we again have retaining holes at the bottom to take care of the retainer attachment.
All right.
So that is about it for our rocket.
Okay. Bob, do you got any questions or comments for the team there?
Yeah, I was just curious about their rail guides, their rail attachments.
Could you please repeat, Bob?
Yeah,
Yes.
your rail buttons. What kind of buttons are you using, and
Uh,
how are you
we are
attaching
using-
them to?
Yeah, we are using the standard 1515 rail buttons, and we are using a M6 bolt to attach it to the centering rings. So both the rail buttons attached to both the centering rings. You can see over here.
Okay.
You can see it. One second. Yeah. So the rail button attached
Ah,
to the centering ring
Okay.
using. Yeah.
How far apart are they?
84 centimeters.
84 centimeters. I need to translate that to inches. So the question I have, or the concern I want to make sure we don't have, I had two rail buttons on a VMAX rocket, plenty of velocity off the rail, but it was a windy day. When the top button cleared the rail, it was able to pivot perfectly around the other rail button near the bottom. So I think they should be no more than like 4 body diameters, 4 calibers apart. I don't know if you can add another one, but just make sure they're not like spaced far apart, because out at Spaceport it gets windy and you can actually throw your rocket. It will rotate and get thrown off the rail at a bad angle.
Right. So let's see. You said they're 84 centimeters apart. Okay, so
That's around 33 inches.
Yeah, 33 inches.
Yeah.
So
6-inch
your
body tube.
6-inch body times 4, that'd be 24. Yeah, maybe it might. Yeah, that's probably a good idea. That's a good idea to move them in a little bit closer if you can.
All right.
Do you have
well,
another
for the
bulkhead?
The thing is, for the calculations and everything, the off rail and the stability, we have kept the effective length of the launch rod only, with considering the effective length at the top, the topmost rail button, and the off rail velocity and the stability turned out to be fine. So
Well, I understand. I had a very high impulse motor too. I mean, we can see, if it's far enough out there for 30K flight, that's fine. I just don't want you to lose your rocket.
Right.
Fine. We'll keep that in mind.
Okay. Anything else, Bob, you want to talk about or ask the team about?
No, I think I'm good.
Yep.
Looks like a solid design. I
Great.
guess you haven't had any test flights, but you did say you vacuum tested the ejection.
We actually tried really hard this time to get launch permissions, but like we had to involve national organizations, and then we were very close to getting to launch. The launch window we were getting is May 27th, but then we had to ship our rocket by then, so we were not able to launch. So that
Okay.
is where the entire problem came out to be.
Have you done ground testing with your ejection charge
Yeah, we have done plenty of ejection tests with both the charge wells and the SRD systems also.
Okay. All right.
Okay.
That sounds good to me.
Okay. So one question, have you already ordered your motor, got a commitment? I assume you're gonna
Yeah,
pick it up
we-
from Wildman at the site.
we already have ordered our motor and paid for it. We have ordered it from Off-We-Go Rocketry. So Mr. Gary has assured he has the motor in possession and he's going to bring it to the competition itself. So we'll take it from there. So we have the motor acquired.
Okay. Are you planning to stay? Where are you planning to stay once you get out to the States here?
We plan on staying in El Paso. This is hotel. Las Cruces. We have our hotel, Hotel Comfort Suites. So we'll be staying there. The entire team will be staying there.
Okay, good. And have you figured out how you're going to get to, both from the airport to the hotel and then also to the site, to the spaceport? You've got transportation lined up already.
Yes, last year our team had rented a car and also we had one driver with us. So
Okay.
we'll be going with the same arrangement this year as well.
Okay, and so you're going to be bringing all of your stuff. You're going to be shipping your rocket, and you're shipping it to the convention to where?
We'll be shipping it to our hotel. So we have it such that two of our team members are reaching on June 9th to the hotel, and the crate is scheduled to come, the rocket crate. It's scheduled to come at around June 10th. So we'll be having our members already staying in the hotel when the crate arrives, the hotel.
Okay.
So we have taken care of the logistics in that sense.
Okay, good. How many of you been out to the spaceport before? For
This year,
competition?
14 people are coming, out of which 4 have already been to Spaceport.
Okay, so make sure you brief each other on what to expect. You're probably no stranger to heat, but it's already shaping up to. I mean, we're going to be close to 100 degrees Fahrenheit here today, and and I'm just south of Las Cruces, so it's going to be really, really hot, and we have not seen a drop of rain since the first of the year. So yeah. So expect that. There is a border patrol checkpoint between Las Cruces and the spaceport, so make sure everybody has the appropriate ID. The border patrol guys have been briefed, and they know to expect you, so should not be any issue. But just make sure you take care of that. So you've got your visas and everything else all squared away, correct?
Yeah,
I
everybody
heard.
has obtained their visas.
Okay. Let's see, and you've got your the team members are going to be especially downrange and working with the rockets. You've got your AAA memberships all lined up already. And don't forget to vote in the AAA elections if you haven't. So that's good. Let's see, fire record. All right, I think I'm right with Bob. I think you all have a good package. You've got all the piece parts for your rockets, so you'll be ready to assemble them. As a reminder, do not plan to paint your rocket in the hotel room. That's we in the past we've had to some teams have ended up paying big bucks to get their get the rooms redone after doing painting or epoxying. So please just don't go there. Okay.
Yeah, the first thing tomorrow we are doing is sending the board use out for painting. So we are all set with that.
Okay, good. So just make sure you've got your all your appropriate gear. I like your team shirts, but I will tell you that black is not a great color out in the desert. You'll see me with light blue fishing shirt on, covering all the way up. And if you look at the folks who actually work outside around here, there's nobody's wearing shorts and flip flops and skimpy shirts. Everybody's wearing long sleeve, big hat, and so forth. So just make sure you take that to mind. And for those who have not been here, there are dangerous critters out there. Should not be a problem, too much of a problem, because a lot of movement around, so probably won't see any snakes, but you might run across them, but just be very careful. Every bush out here has something that'll stab you, so do that. A couple years ago, we have a wasp that's called the tarantula hawk, and it's black with orange wings. It's a huge sucker. And a couple years ago, we had a swarm of them right by the right by the recovery area. And they're not normally aggressive, but I will tell you that being stung by those, that's the worst insect sting in terms of pain that there is. So if you see, big black or alien looking flying bugs, do not mess with them, or anything else, because
Yeah, we keep that in mind.
yeah, oh yeah, no, you will not be a happy camper. Okay, well, I don't really have anything else. I think I think I agree with Bob. It looks like you've got a good package. You've got everything. You've thought through the big details. So we're looking forward to seeing you. Make sure stay safe out there. Be careful. Coming and going, and but above all, have fun and have a great competition.
Yeah.
Okay. Any last words, Bob?
No, all good advice.
Okay. Okay.
Yeah,
All
sounds
right
good.
then.
We had a few doubts. If you could ask.
Yes, certainly. Yeah. Go for it.
Yeah, so we were wondering if we could receive a review for the technical report because this time we have put in a lot of effort into analyzing different simulation methods and basically in ensuring that we have everything ready for the change to this category. So if we could receive a review about our technical report.
Yeah, that'll be up to your individual judge. We are, I know Anita Jimenez, who's the new Director of Competition Operations, is working really hard on figuring out a good way to get feedback to the teams on the technical reports. But, quite frankly, they haven't come up with a good thing just because of the way the scoring goes on Hero X. It's very, very difficult to extract that stuff. It has to be done, all by hand, and which is fairly long. In the Hero X interface is basically user hostile. And so we have to figure out a good way to do that, and we just haven't done it yet. But this is one thing that we are stressing with the judges is in some fashion to make sure that you get good feedback from your technical reports. How soon or in what form that'll come, I don't know. I can't tell you right now.
All right, thank you for letting us know.
Okay.
We also had one more doubt about the flight safety review at the competition.
Yes.
So for us to fillet our fins with the body tube, we require to put the motor inside the side-in assembly. And
Yes.
as we all know that we're not allowed to carry energetics inside the place, the exhibition center.
Right. You can't bring your motor in
How
there.
do we go about doing the fillets, or do we do fillets after the initial flight safety review?
That's a good question. I'm going to have to defer that to. Let me take a note on that, and I will ask Ken Overton, who's the flight safety guy. So, so you basically, let me just make sure I understand the issue here, that you have to have the motor in order to
Yeah,
fasten
so-
everything together and do your
So-
external fillets.
Yeah,
Is
this
that,
is our basic motor bay assembly. We'll be having a motor inside this. From the aft end of the motor bay, we'll be sliding this inside. So we
Okay.
can, for us to show everything, we can not have the propeller inside the motor. We can only have the motor casing, that will be all right. But for us to be able to do the fillets, we need to have the motor ready inside.
or, yeah,
That
or at
is one
least your,
concern we have.
yeah, so you at least have to mate your fin can with your aft body tube. You don't necessarily need the motor itself in there. You just need the fin can epoxied with the fillets into the body tube. Right? Can you do that? You can do that without doing your motor. I mean, we don't have to have you take it apart for us during that safety review. If you've just got the internal stringers in your fin can with your aft body tube on it, then you can just make your fillets, with that way, and don't put your motor in there. Just leave the motor out, and that would be acceptable during the safety inspection.
All right, we'll look into that.
Okay.
Yeah, so that is all about, that is it from our side.
Okay. Very good. Any last words? Y'all have done a great job. Very, very impressed with your work. Looking forward to seeing you out at the Cup.
Likewise. Thank you.
Okay.
Thank you.
Okay. Thank you. Okay.
See
We'll see you all
all
later.
Okay. Bye.
Bye-bye.
Bye.
Bye-bye.
Recording.
Stop the recording.